stuff. I know there's a lot of information here being thrown at you. Hard to keep up with it.
Are you only going over chapter 1?
1 and 2. The next two. A little more about the addressing. Maybe some of you ran across this. So I have an input, let's say input byte 1, bit 0. If I append that with a colon P, anybody run across this? What's the colon P tell the PLC to do?
Stop it? Something like that?
Yeah, it's what it does is you append it with a colon P and it says, okay, I want immediate access to the IO. So instead of, and here's what happens, right? We have all these inputs. The PLC scans the inputs, and the status of the inputs are put in the image table, right? Here's a little bit of a difference too. In the Allen Bradley world, this is the input image table. In the Siemens world, it's called the process image input, PII. So the PLC scans the inputs, it places the status of the inputs in the image table, and then that goes into the CPU. You append it with a colon P, and it bypasses the image table. So we're getting data directly from the input monitor. The reason you might want to do that is what happens with the image tables is they only get updated every scan. Whatever the length of the scan time is, the image tables get updated once per scan, right? But we could have a fast changing input that might be changing before we get through a complete scan, right? So this way the CPU goes directly to the input and grabs the data right from the input monitor. Same way with outputs. So if we wanted immediate access to outputs, colon P. Instead of going to the, and this is called process image output. The book calls this PIQ, Siemens documentation on PIO, whatever. PIO, PIQ, whatever. Process image output. So instead of going to the image table and then updating the outputs, it updates the output directly.
So if you want to skip the one of those, you put a colon P in that.
Program organization. It's the same stuff in Allen Bradley. Different buzzwords. So we have linear programming. What's the other one? Anybody remember?
Modular.
Modular. Good, Joe. And modular programming. You know what the difference is?
Linear is the one that you, whatever it comes with it, that's what you get. Modular you can add. No?
No. So in linear programming, you have all your programming in OB1. It's just like putting everything in the main routine or everything in latitude.
It's a giant mess.
Giant mess, there you go. I'll put it like that. In modular programming, everything, here's OB1. And then all these code blocks are called into OB1. Just like doing a JSR, right? Jump the subroutine, jump the subroutine, jump the subroutine. Except, here's the Allen Bradley world, jump the subroutine. Siemens world is a call. Just like in the robotics world, right? Didn't you guys call routines in the robotics world?
Yep.
Same thing, except we're calling blocks. So we're calling it a subroutine. And maybe this subroutine calls another subroutine. Calls another block. Modular programming, it's the same thing as using subroutines.
Mr. Ham, how detailed did you want those answers on?
I had 4 pages I had to do.
This, like I said, this book is really, it's a hard read. It's hard reading this stuff. I do better going to the Siemens documentation than I do with this book.
I just kept it simple when I was writing the answers.
Yeah,
I didn't want to
yeah.
spend time and wasting space.
Good enough, yeah.
Problem I had with a lot of it was, I couldn't figure it, I mean, to see what they were asking, and I'd read over, and a lot. Maybe this is what they want.
All right. Let's look at, let's see here. If you look at chapter 2, page 60, we'll look at a couple of those.
What?
And then, page 60? Yeah.
Your ears were burning when I got to that one.
What's it?
Your ears were burning when I got to that one.
Oh, yeah. It says, describe each part of the following tagged addresses. I-0.6. Most of them do this now.
Inputs, swap.
50.
50, swap.
Bits.
Yeah, input, byte, bit. Q, 2.3.
Output, byte, bit.
Output, yeah. Byte, bit, yeah. I-12.6, is everybody good with that? Input, what byte? 12, yeah. QW112.
Output word.
Yeah. Output word, starting byte 112. IW96.
Input word 96.
Yeah. Input word 96. Starting byte address 96. And you'll see this once we get into analog more, because what happens is we have several analog addresses. And here's why this is important. This output, it takes up bytes 112 and 113, right? Why do I say that?
No, it's a 2 bytes. One stays on, one stays off.
Yeah, there's 2 bytes, right? Because this is a word database address. That makes sense? And a word contains 2 bytes. Clear as mud?
So if it was a double word, it would make 12, 13, 14.
Yeah, yep. Yeah, good point. So what can happen is, let's say we try to address byte 113, but we have an analog device here. See what's gonna happen? It's gonna walk on the data, right? So if we try to address byte 113 in some other tag, let's say we do something like this, IW113. That's gonna create a problem.
Because you're mixing an input with an output.
That's right.
And then you don't know, the
Exactly.
module doesn't know what's activated.
That's right. We're using the same byte address, so we're gonna be walking on the data that's here, or vice versa. Let's see.
So how do you solve that? If you go into the address and you override it and make it out of the output.
Yeah, you would make this a different byte address. Just make that a different byte address. And here's the problem, the software won't tell you. It's your.
So it's like B300 and B301.
Yeah, it's about like using duplicate outputs. Yeah. MD48. What is it?
Memory double word.
Memory double word, starting byte 48. So how many bytes does this actually take up?
4.
Takes up 4 bytes. 48. What's the other ones?
49, 54.
51. I 8.5, colon P.
And for the 5, 8, bit 5, but it's going to skip stuff. We'll put that.
Yes. Immediate access to IO. There we go. Immediate access to IO. Q 2.6, I think everybody's got this by now.
Not
Colon P.
immediate access.
IW0,
Input word.
little word, yep, starting byte 0, QW2, everybody's good with that. And this temp 5, did anybody run across that?
Yeah.
So we have a tag that was created, the tag name is temp. But temp5 is part of an array. Does that make sense? So an array can be whatever length you want to make it. So this started at temp. Here's what happened. This array, and this will all come clear here in just a second. This array started with, let's say we made an array of 10. We made a tag called temp. But we set the array dimension to a value of 10. Remember it when we set up the dimensions in Allen Bradley?
Yeah.
That dim 0, dim 1, and so on. We set it to a value of 10. So that means our tags, temp 0, temp 1, temp 2, that makes sense, down to temp 9. That's the tags that are going to be in that array. This temp 5, it falls within that array, right? So it's a tag in this array. Temp 5.
So what does temp mean?
That's just a tag name.
That's good.
Yeah, that's like my tag, your tag, Jimmy's tag. So
This
it's,
tag.
Touch.
With the tag.
Really?
So this,
Yes.
Uh,
when we do this temp thing,
Come on, Jimmy.
are you saying that versions of a particular tag, so that you've got 5 different scenarios and 5 different
What?
outputs?
hey, Joel, give me 5 minutes, we're gonna take a break. Unless you have a. Okay. Yeah, 5 more minutes, we'll take a break.
Awesome.
Yeah, that's just, yeah. We set up this array, just like we did in Allen Brown. Remember we set the array on, maybe some time, we made 5 timers in an array? Let's see what else, real quick.